Okay, our final speaker is Sagnik, who's going to tell us about graph connectivity using star contraction.
Thank you very much. Thanks to Sanjeev and all the other organizers. It's a wonderful workshop. I'm going to talk about graph connectivity in this talk, but the message that I want to talk about is how hard it is to shave off log factors, essentially. This is a joint work with Simon, Troy, Yuval, Powell, and Danupon. This has appeared a couple of years back in Fox. All right, so let me first introduce the model of computation that I'm going to talk about, which is a bit different from all the computational the models that we have seen so far. And although the main message of this talk is not about the model of computation, having such a concrete model helps, actually. So this is the model. It's a query model, and it's called cut query. So let me first try to define the model, and then I will give you some motivation as to why this model is interesting. So you have a graph, which is you have some oracle access to, and you can query a set of vertices, and it will give you the value of the cut, which is identified by that set of vertex. Not just the value, not the edges, and that is important. And in this talk, the goal is to find a minimum cut of the graph. I mean, if the minimum cut resides as a degree of some vertex, it's very easy to solve. You just cut all the vertices and just give the minimum amongst them. So essentially, we will always assume that the minimum cut is not a degree cut. It's somewhere inside. And throughout the talk, we will use delta as a minimum degree and lambda as the edge connectivity of the graph. So for example, if this set comes along, the answer is going to be 4 because the 4 edges are going to be cut here. Right, and even though there are 2 to the power n cuts that you need to search over, there is an pretty much trivial algorithm that only queries n square or order n square many queries and gives you and solves any conceivable graph problem, right? And I will get into what this algorithm is. It's not very hard. Essentially, it shows that the cut query is at least as powerful as edge query. Right. The motivation comes from the classical problem of submodular function minimization, and I thank Andrew for introducing what is a submodular function. So I'm just going to make it go over it faster. So f is a set function which is submodular if it is working on an universe and it assigns values over the sets, and it has got the property of diminishing marginal gain. So essentially, think of it as like you go to a restaurant, you order some items, and if you order chips and if you order a drink with it, you pay for the drink. But if you already have a drink, then you get a free refill, so you pay less. That's the idea. And because even to specify the function, you need exponential size. You usually do not look at it. You usually look at this function from an evaluation oracle perspective. So you have query access to this function. And the goal in this talk is going to find a minimizer of this function as opposed to a maximizer, which Andrew talked about. Now, this kind of function shows up almost everywhere in any field that uses some sort of combinatorial optimization. So for example, for today, we're going to talk about graph cuts, and it's not very hard to see that graph cuts are also submodular function, and the min cut problem is just a submodular function minimization problem. So just to see whether how this inequality holds, this is just a proof by a picture kind of thing. There are 2 cuts, A and B. If you look at the intersection and union, you see that this red edge is counted twice over here, but it's not counted at all on the right-hand side. So, and all other edges are counted once on both sides. So that's sort of like a proof by picture. And also, one subclass of the submodular function is important to us, which is called symmetric submodular function, and which is sort of when you are asking for the global minimum cut. The symmetry being that cut of A is going to be equal to the cut of its complement set. However, there is an obvious answer, obvious like minimizer to this question. You just output the empty set or the whole graph. So we are not looking at the minimizer, we're looking at a non-trivial minimizer. And there are, as opposed to it, there is asymmetric submodular function minimizer, and that's going to be the ST version of the cut problems, and which is also max flow and matching and this kind of problems. So I want to point out one thing is that we know how to solve this in polynomial time. It's not, we are not looking at an NP-hard problem here. And this, it's an old result by Groschel, Lovesh, and Shriver, who shows that this is essentially, by a beautiful reduction, shows that this is essentially a convex optimization problem, convex minimization problem. And we know how to do convex minimization. So you do get an n to the power 5 upper bound, n being the size of the universe. And this has been improving steadily over the last 30 years or 40 years. However, one of the things, and right now, this is the state of the art. You can do it in n square for any submodular function. Of course, for graph cuts, this is sort of like a meaningless bound because you can solve it anyway in n square thing, n square queries. Right. So, however, for global min cut, if you use any of this algorithm, it's just going to give you 0 because there is a minimizer. So there is, it would be nice to have some sort of adapter which you can use to plug in one of these submodular function minimizer algorithm and get, and you will get something like a non-trivial minimizer of a symmetric submodular function. And that indeed is there. This is extending the work of Deb Malia and Jason. And we observed that you can actually do symmetric submodular function minimization by the similar runtime. However, the lower bound is stuck over here at omega n. Yeah. Yeah.
So it means that if you have any algorithm for trivial submodular minimization, you get one also for non-trivial.
The lower bound side is not so promising. So there is one lower bound from 1988, which gives an omega n lower bound for symmetric submodular function minimizer. And then randomized is only n over log n. And very recently, the deterministic lower bound has been improved to n log n. So that's where we are at. Lower bound situation is dire. And because it turns out to be a harder problem than what I have imagined when I picked up this problem, so we are now in the search of a good candidate problem which can prove high submodular function lower bounds. Any lower bound, randomized lower bound, which is omega n, little omega of n, even n log n is good for us at this point. So, well, min cut might be such a problem because let's look at the previous work. So connectivity, graph connectivity, whether the graph is connected or not, there is an n log n upper bound. It's an old upper bound. And then in the last 4 or 5 years, there are 2 results where you can actually show that the minimum cut itself can be computed in n log, polylog n number of cut queries. From the lower bound side, we have n over log n, as I just mentioned, and Sefer has proved an n log n over log n lower bound for minimum cut over simple graphs, and that's where we are at. So it's conceivable that the min cut itself is going to be such a problem for which we can prove a lower bound of, let's say, n log n, cut query lower bound. And all of these algorithms over here are combinatorial, and this is important because the submodular function minimization algorithms are not really combinatorial. These are convex, very analytic lower bound, upper bounds. So that brings us to the result that I'm going to talk about. It's a negative result. It says that randomized cut query algorithm for min cut in simple graphs is order n. There are no log factors, so you cannot hope to improve it. And this is actually not even known for connectivity, graph connectivity. So this also gives you an order n upper bound for connectivity. And we believe this is tight. We don't know how to show it at this point. There is still a log gap, but if we believe conjecture by BFS in 1986, then we sort of it's a tight result. And this has got other applications as well, but I'm not going to talk about those things in this talk. I'm going to only focus on this theorem. And as far as the technique goes, there are only two main components here. One is a star contraction, and another is something called separating matrices. If I just use separating matrices, you already get an order n for connectivity. If you combine it with star contraction, you get an order n min cut. So let's go over them one by one. I will start with star contraction. So what can we do with cut query? You can check an edge UV is present with just 3 cut queries. This is sort of shows that cut query is at least as powerful as edge query. So if you get this edge, if you want to check whether this edge is present, you're going to make this cut a cut of 9, a cut of 3, and cut of everything other than 9 at 3, and do some subtraction. You get to know this. More interesting is that you can also do this thing that you can find with an edge. You can find an edge between one vertex and a subset of vertices. Of course, 3 cuts is going to give you that there is an edge present. To find it, you have to do a binary search, and that's why it's going to take log n queries. And this already gives you a spanning tree computation with n log n many cut queries. You can also randomly sample an edge. This is a similar kind of operation that I mentioned, the binary search, but when you do the binary search, you do this partitioning randomly. So any edge, picking a random edge incident on a particular vertex, it needs log n queries. And because you know the degree by making n many cuts, you can find any random edge of the graph with n log n queries. And also, one of the interesting thing about this kind of query is that this can work on graph minors. If you know what edges that you have deleted from the graph or what you have contracted, you can sort of do the cut queries in the original graph, subtract some numbers, and pretend that you are working on the graph minor. So suppose you want to sample, out of all the n squared edges, you want to sample uniformly random one edge.
So it's like n plus log n?
Yeah, n plus log n, right. Right, so what is a basic algorithm to solve this? You know that the min degree is at least min cut, so you just pack min degree many spanning trees in the graph. And we know that each of the spanning trees, or forest in this case, maybe, must cross every cut at least once. So if you can get those spanning trees, you can just compute the min cut in the graph that you have gotten. Now, the complexity of this is going to be delta many spanning trees, and each requires n log n, so n delta. And you can make it just n delta without any log factor by using something called separating matrices. I'm going to come to that. But let's say we have it. If you want to pack t spanning trees, you need tn many cut queries. Now, the question is that can we do any better? As it turns out, there is this amazing framework, first started with Ghaffari Thorup, and there are multiple ways of doing this thing, which says that if I give you a simple graph with min degree delta, then you can pick some super vertices of this graph. Let's say v1 to v whatever, and number of super vertices is going to be n over delta. And the number of intercomponent edges over here is going to be order n. And the property of this clustering is that all the min cuts will be preserved by this clustering. Now, if that happens, and if we can somehow find this clustering, we can just work with the contract. We can contract each of those clusters, work on a smaller graph, and then we have an n order n algorithm, right? Because there are n over delta many vertices, you pack delta many spanning trees, so n over delta times delta is going to be order n. The question is, however, how do you get this clustering, right? So one of the ways you can think about it, and is something called related to graph percolation process. So you think of a min cut. Fix your favorite min cut over here. And for every vertex on the graph, choose one of its neighbor uniformly at random. Right? And you can show, okay, so the purple edges are the sampled edges that you have chosen. And you can show that the sampled edges will cross the min cut with very small probability. So it will not. And one of the ways you can see that is for any vertex, it has got fewer edges that is crossing the min cut than it has got other edges, right? So if I randomly sample, I will mostly sample on its own side than across the shore, right? So in this example, you have got 4 vertices, which actually matters. And for each one of them, it will not cross the min cut with probability at least half, so you get 1/16. And this is constant probability. But in a more general case, what you're going to get is the following, right? So for every vertex V, which is the neighborhood of the cut C, you're going to get that how many edges are crossing the cut divided by the degree. This is the probability that it crosses the min cut. So 1 minus this probability it does not cross. And you multiply over all the vertices. And you also have this kind of constraints that C of V over D of V is at most half. This is the constraint that I mentioned. And if you sum over these ratios, you get at most 2. If I have this thing, then essentially you can show that this is a minimization of a continuous concave function over a convex set. And this is going to be bounded by a constant probability. This is actually one of the extremal points where the minimizer resides. Yeah? Sorry? Yeah. Yes. I'm only going to talk about non-trivial min cut. Right, so that is promising. So you can take the graph G, do one-out sampling, contract those edges that you have sampled, and you never cross the min cut. So you preserve all the min cuts, and then solve on the graph that you have gotten by contraction. But you can show that it doesn't really reduce the number of vertices that much. This is something I've written when I did this slide 2 years back. I don't now remember the example of it, but you can have an example where n over square root delta over the vertices. The intuitive idea is that a min cut, yes, you will never cross it, but there can be other cuts which also, if you do it only once, you will not cross. Because most of the vertices that is taking part in the cut looks like it is behaving like a min cut, but there is 1 or 2 vertices which makes it not a min cut. So you will not also cross that with good probability. So Ghaffari, Mohsen, Christoph, and Mikkel showed that if you do it twice, then you get what you want. You get n over delta. There are no logs over there, and the complexity is going to be, if you have that, you have n over delta many vertices, then now you pack your trees, you get order n. There are some issues with it. Let's say the cluster diameter is actually log square, which is not a big deal. You can still do distributed computation on it. Analysis is a bit dodgy, in the sense hard, but this gets the job done. So we are done, right, at this point. The problem, however, is that how do you do the two-out sample? You can, of course, do it in n log n, because you can sample edges with log n, and there are n vertices on which you have to sample, so you have to somehow get that down. So this is sort of our contribution, is that this whole percolation process or the random process need not be so expansive. You can do this random sampling in a much smaller graph and still get the job done. And here is how it works. So for example, this is what I do. I will construct a set R where it's a random set R where I pick vertices in this set with probability log n over delta. These are my spatial vertices. Let's mark them with red. And for every other vertex, I'm going to look at its neighborhood, look at how many of the spatial red vertices that I have in the neighborhood, and amongst them, pick one at random. So this is something, once you have done that, you have a bunch of stars which is hanging from each of the red vertices. How many stars do you have? By definition, there are log n over delta, n log n over delta many stars, right? And because these red vertices are sampled randomly or uniformly at random, you still have this property that you will see less number of red vertices on the across the cut than on your side. So that immediately controls a number of the vertices, but there is still log n factor over there. And so the complexity now becomes n over delta log n times delta. So you have n log n. So you have sort of, yes. Yeah, so that's a very good question. It's a first attempt, so the log n is to hit every vertex. The neighborhood of every vertex. Yeah, so union bound essentially. Right, so you get n log n. So you sort of recover the result. But you still have this log n factor roaming around. So let's try to do a little bit restricted sampling. So now we are going to sample with log delta over delta. Now, we are sure we are not going to hit everybody because we don't have n factor over there. We cannot do union bound. But how many we do not hit? That you can bound. That the number of the vertices which has got no neighbor in R is going to be bounded by n over delta. So you can just treat them as your super vertices. At this point, it doesn't hurt you. So you have the R, which is a sample set, which is n log delta over delta, and the other sets are n over delta. And now you sample over here. You do the star construction over here, and you get n log delta many queries in the end. Now, it really makes sense when delta is at most polylog n over here, because if delta is really large, n over delta itself becomes really small, so you can do it in order n. So if delta is more than polylog n, you can use some other subroutine to get it down to order n. So only regime that is really interesting is delta is at most polylog n. So you get n log n queries. And I have to say at this point that n log n is what I'm going to show you. I'm not going to show you n at this point. But there is, again, I have cheated at some point, is how do you do this? Again, how do you sample the vertices over here? And for that, we need the other tool, which is separating matrices. So what is the problem? If we abstract out the problem, what is the problem? You have a vertex set V prime, and for every EU that is not in V prime, it has to independently sample a neighbor in R of U, essentially. V prime is the set which you do not touch, essentially. So just at this point, recall this is the property we need for the min-cut algorithm to work. We need, as long as we have these two constraints and we are working with this kind of optimization problem, we get a good probability that we will preserve all the min-cuts. This is something we also have to take care. We do not want to cross the min-cut. So we can sort of parameterize this. We can call that alpha beta, something is alpha, random process is alpha beta good for contraction if this following two properties hold. Essentially, I'm going to replace this with alpha, this with beta. And if we replace alpha and beta, this is going to be the probability that it will not cross the min-cut. So let's work with that. Any alpha which is less than 1 and any beta which is a constant is good for us. So this is the problem. So you have your red, your sample sets. You want to sample uniformly. Let's make it even more concrete over here. Two sets, S and T. Let's say both are for size n. And from S, you want to sample uniformly in T. Trivial is n log n. How can I make it n? let's look at an easier problem where you do not sample, but you find one neighbor. Now, let's, for the timing, assume that every vertex on left-hand side has degree bounded by L. So essentially, this is a matrix problem, right? You can think of this side as the rows of the matrix, this side as the columns of the matrix, and you have row sparsity of L. And you have to essentially, let's say you want to learn L. And for the timing, to think of L as a constant at this point. So there is a way to do it, and we show that how to do it, that you really have to use the property of the power of cut query, in the sense, so far we have only used, whatever we have done, it could have been done if instead of giving the value of the cut, it would have, if it would have given just whether the cut has one edge or not, at least one edge or not. So a decision version of the cut query was also fine for us at this point. But cut query gives you the value, so that's log n bits of information. So you have to somehow use that, and you can use that to get it down to order ln. Now, given that, this is what I explained over here. Given that, you can do some sort of L0 sampling, Andrew's paper on L0 sampling, that kind of thing. So you can bucket the vertices on the right-hand side based on its degree. And for a degree bucket of 2 to the power I and 2 to the power I plus 1, you can subsample T so that you only have constant many neighbors on the left-hand side. So, and then you can sample, then you can use the separating matrix to learn it. Of course, the question comes is like, okay, this is you are learning it, but now you have to sample within it, whether it's going to be a good sample so that it preserves the main cut. And we can show that essentially if you sample this way, because you are not preferentially treating anybody, it remains alpha beta good. It's a sort of symmetric argument. Now, that will fix this bullet point, and you get order n log n over here. And I will just take one slide to give you one sentence gist of how to go beyond n log n. So you need to have n over delta vertices with order n complexity. So far, we have n over delta log delta vertices with order n complexity. To go from n log delta over delta to n over delta, you essentially, again, use separating matrix, learn a densen up subgraph, and do a 2-out contraction within it. So this is a very small part, but the majority of the work has already been done. So this is sort of engineering at this point. So that gives you that. To summarize, this is what you have. The open problems are very interesting, and I would be very happy to see what your thoughts are over here. The open problem is essentially all the lower bounds that we have seen so far comes from the lower bound from communication complexity. And in communication complexity, just to prove a lower randomized communication lower bound for edge connectivity, which is n log n, is an outstanding open question. We know how to prove n. Sefer showed how to prove it n log n. N log n, we do not know. To make this algorithm zero error or deterministic is also an interesting question. And for weighted graph, we are far away, in the sense it's like the state of the art at this point is the upper bound of n log to the power 4n. It can very well be order n, or it can be an example where you can show a submodular function minimization lower bound. I will not bet on that. It might be on order n. And in general, proving any omega n evaluation query access lower bound for submodular function minimization, I think, is an outstanding question that should be solved. N to the power n log n is good at this point. That's where I will stop. Thank you.
And I also just, so this concludes our program, and I hope you all enjoyed the workshop. And I just want to say a few quick words of thanks. So first of all, thanks to all the speakers for the really interesting talks that we have heard over the past 5 days. And I want to thank the Simon staff which did a lot of hard work behind the scenes, handling all the logistical details, and Ashley, Caroline, Francis, and other members of the Sanders team. And I want to thank our videographer, Omid Far, who was here from beginning to end, helping every speaker set up. And I think all of this really contributed to a very successful workshop experience. And finally, thanks to Ronit and all the co-organizers for creating the Sublinear Algorithms program, which ultimately made this workshop happen. So thanks, everyone.
And thank you to Sanjeev.